In the next few slides, we're going to look at the design methodology and software tools for FPGA development. This diagram shows a typical programmable logic design flow. We start with design specification, which describes the properties or the functionalities of your intended design. And then we describe the design using RTL coding, such as vhdl or verilog. Engineers will describe the behavior or structural description of the design using vhdl or verilog, and possibly with the help of other high-level tools to speed up the design. Then, taking the design, the engineers will perform RTL functional simulation using tools like Mental Graphics Model Sim or other third-party tools. This step is to verify the logic function and the data flow of the design. It does not intend to verify the timing properties. The next step will be synthesis. During this step, engineers translate the design into device-specific primitives. For example, if the design requires floating-point operations, DSP modules will be required. Also, during this synthesis step, we'll perform optimization to meet the required area and performance constraints. We'll make decisions on how many logic elements we'll use, what kind of memory blocks we'll use, and also the number of I/O pins required. For Intel FPGAs, we'll use Quartus synthesis tool or other tools available from third-party vendors. The result of the synthesis step is the post-synthesis netlist. Next step is to map these primitives to specific locations inside a particular FPGA. And this is called place and route, or sometimes also called fitting. When we map these primitives, the tools try to respect the area and performance constraints. You can specify routing resources to be used. The result of this place and route is the post-fit netlist. With this post-fit netlist, we will know exactly which logic element on the FPGA will be used in this design and how these resources are connected using interconnects. Next, we perform timing analysis to verify the performance specifications. For example, we want to make sure that this design will run at the clock speed that we desire. Finally, we'll load this design into FPGA card. We can use simulation or program into the device to test the design on the FPGA board. And with Intel FPGAs, there are on-chip tools such as signal tap we can use for debugging the signals on the hardware. For Intel FPGAs, Quartus design software is the tool we use to perform the design flow. We start with certain system description, and we know what kind of modules we will have in this design. We also know in the I/O pins we use for input data, output data, and the control signals. We'll then use HDL, high-level description language, to describe these modules. This HDL or verilog code can be put into Quartus design software, and this design software is a fully integrated development tool. You can use multiple design entry methods using vhdl or verilog, or using IP cores provided by Intel or third-party vendors. You can use Quartus software to perform logic synthesis, place and route, and then timing and power analysis. Finally, when your design is completed, you can use Quartus software to program the design into the actual FPGAs.